Okay, let's get started. And so this is the first official seminar this year by somebody other than me, the director of the SDC for Integrated Quantum Materials. We have a really outstanding group of speakers this year, and for those of us listening to us on YouTube, these will all be streamed on YouTube, and you can watch them in real time wherever you might be. You can also, we have a channel on YouTube, which actually works, that you can go and see the talks of anybody that you're interested in at any time that you like later. And so it's like a library, and good old YouTube actually operates correctly. And so it's a good way to learn about other topics too. So please take a look. Today we have Dahlia Klein from Pablo Guerrero's group at MIT. And she's an advanced grad student. Will be looking for a job sometime in the not so distant future. And this is a great opportunity to see what she's been doing. The topic is something that's, I think, a very exciting topic, is that two-dimensional materials turn out to be really tough. At first, people thought they would entropically explode into dust or something like that, which seems to be just opposite the truth. And they're actually extremely tough, and they like to be separated into things that are only one atom or molecule thick. And the excitement now is to stack these up into heterostructures that would look like molecular beam epitaxy, except there you can't make it so thin, but here they're only like one atom or molecule thick, and it can be made out of different materials. And so one of the things you would like to do in the modern quantum world is to actually polarize electron spins or maybe form edge states in the material. And to do that, you need magnetic materials. And so one thing that Dahlia has been doing is to develop very thin layers of magnetic materials that are not conventional but can really work in that game. That's what she's going to tell us about today. Thank you.
Thank you for the introduction, and thank you for inviting me here today. So my name is Dahlia, and I'm a grad student in Pablo's group, and I'm really excited to tell you about some of the work we've done in the past several years on magnetism in the ultrathin chromium trihalides, a new class of magnetic insulators. So in my talk, I will first give an introduction to 2D materials and move on to 2D magnets. I'll then discuss magnetism in chromium triiodide and ways that we can control and detect the magnetic states in these ultrathin crystals. I will then move on to magnetism and structure in chromium trichloride, another member of the chromium trihalide family, and conclude with outlook for where 2D magnets will go from here. So while many of you in the audience are familiar with 2D materials, I will introduce it for those who may not be as familiar. So 2D van der Waals materials consist of crystals that are easily cleaved along what's called the van der Waals gap. So the bonds within a layer are much stronger than those that separate the different layers. And so they have several advantages. So they're atomically flat, they're substrate independent, they're gate tunable, and most notably, they're stackable. So when we say that 2D materials are atomically flat, we really do mean down to the atomic limit. So if you take a conventional silicon wafer with silicon oxide layer on it, there's actually quite a lot of surface roughness, as well as some dangling bonds and free radicals at the surface that can interfere with your device that you fabricate on top. In contrast, if you take, for example, boron nitride, which is a very good 2D insulator, then it really is atomically flat and can screen some charge impurities and other things from the silicon oxide if you place a layer on the bottom below your graphene device. Van der Waals materials are also substrate independent. So if you want to perform epitaxial growth, you have to think about your underlying substrate and the crystallographic orientation. And there can be concerns about lattice mismatch that introduce strain at the interface. Whereas with van der Waals materials, we really have the freedom to choose whatever substrate we want. So here's just showing graphene on a flexible PDMS substrate. And so we really can pick these layers up and then place them as we please on whatever final substrate target. They're very gate tunable, so if you take a 3D material, such as the cuprates, and you want to change its properties, you generally have to dope it by substituting one type of chemical atom with another one. However, with 2D materials, since they're so thin, they're very susceptible to gate voltage, and so you can control their electronics, superconducting, magnetic properties, and so forth, just by applying a gate voltage, and then you have a very tunable device, rather than having to grow a series of different crystals with different stoichiometries. And this is some examples. Here's a monolayer molybdenum disulfide transistor, which has a 10 to the 8th on-off ratio, so it's very, very sensitive to gate voltage. Also last year, our group demonstrated that monolayer tungsten ditelluride can be gate-induced into superconductivity, which has also been observed in other layered materials. So you have a very wide range of materials parameters that can be tuned in a single device just by applying some volts. And finally, van der Waals materials are stackable. So once you have a few properties that you want to combine, you can just stack them on top of one another in these atomically sharp, precise interfaces. So here's a cross-sectional TEM of a boron nitride, graphene, boron nitride stack. And you can see that they really are an atomic placement with one another. And more recently, there's been a lot of attention in the twist degree of freedom. So if you have some epitaxial growth, you don't have the flexibility to twist the layers with respect to one another, but van der Waals materials offer this tuning parameter, and so our group demonstrated last year that if you take 2 layers of graphene and place them at the magic angle of 1.1 degrees, you can access this beautiful phase diagram by applying gate voltages and access superconductivity, Mott insulating states, and even ferromagnetism. So there's a lot of room for exploration now that we have this additional degree of freedom in these systems. So the family of 2D materials has really expanded since graphene was first isolated in 2004. So now, in addition to graphene, we have other semi-metals such as tungsten ditelluride. We have insulators like boron nitride. We have a long list of semiconductors, including molybdenum disulfide, as well as superconductors like niobium diselenide. And we even have topological insulators that can be exfoliated, such as bismuth selenide. However, until just a few years ago, one notable absence from the family of 2D materials were magnets. So in the past few years, there's been a surge of research in the field of 2D magnets. They can now be classified in different materials classes. So we have insulators and semiconductors, such as the chromium trihalides, like chromium triiodide here. We also have the CRX-TE3 family, such as CGT, shown here. And a little more recently, we began to have conductors as well, such as FGT, shown here. And this is certainly not a complete list, and it's constantly growing every week. And so there's a lot of more materials to explore that are predicted to have magnetic order that persists down to the few layer limit. For the rest of the talk, I'm going to focus on the chromium trihalides, which are a class of magnetic insulators. So the chromium trihalides share a common crystal structure, where we have a chromium 3+ honeycomb structure, shown here in the purple spheres, surrounded by a halide octahedra in the silver balls. And so each monolayer is stacked upon other monolayers and are separated by the van der Waals gap, which makes this a naturally layered, cleavable material. They all undergo a stacking phase transition in which the bonds between the chromium and halides don't really change, but the stacking between adjacent layers shifts dramatically. So here I'm omitting the halides and only showing the chromium honeycomb structures for 3 adjacent layers. And you can see that at high temperatures, there's this monoclinic stacking where the layers shift along the A-axis. And then below the structural transition, which varies depending on the material, it adopts this rhombohedral ABC type stacking instead. The magnetic order can be understood by thinking about localized moments on the chromium ions. So chromium 3+ has 3 free d electrons, and we can think of it as being in a roughly octahedral coordination with the halide ions. So in the octahedral crystal field picture, this gives us the T2G and EG splitting of the d orbitals on chromium. And since we have 3 unpaired electrons, we expect to have them filling the T2G half-filled shell. And this picture is consistent with observed saturation moments of about 3 Bohr magnetons per chrome site in the chromium trihalide. The ordering itself will actually depend on which halide ion is present. So in chromium iodide and chrome bromide, there's out-of-plane ferromagnetism. So within each layer, the spins will point perpendicularly out of the plane. And then the ferromagnetic interlayer coupling gives a net ferromagnetic moment. In contrast, chromium trichloride is an in-plane antiferromagnet. So within each layer, the spins will order in-plane ferromagnetically, but then antiferromagnetic interlayer coupling across the van der Waals gap gives rise to an overall no net moment and antiferromagnetic behavior. So in our lab at MIT, we like to study what happens to crystals as we take them down to the ultrathin limit. So we begin with bulk crystal growth of chromium triiodide and chromium trichloride. We then can use Scotch tape to mechanically exfoliate them down to the monolayer or few layer limit. And then once we have identified these crystals, we can then fabricate devices and measure them in a variety of different ways. So I'm going to begin with this discussion on chromium triiodide. So we can grow chrome iodide by the direct vapor transport method, which is a type of chemical vapor transport. So we place chromium and iodine inside a sealed evacuated ampule, and then we place it in a 3-zone furnace where we assign a temperature gradient that gives rise to vapor transport that ultimately nucleates and results in chromium triiodide crystals. These crystals are rather platelet-like, and as you zoom in further and further along the edge of one of these crystals using scanning electron microscopy, you can see that it looks almost like the pages on the side of a book coming apart. So this is highly suggestive of an exfoliatable material that has a strong van der Waals character. The bulk magnetism has been previously studied and shows a strong magnetic anisotropy favoring the out-of-plane axis. Yes?
When you grow it, is it tricky in that there's a layered structure, but there's some that's not layered at all? Or does with, you know, if you magically come down the right way, without pain?
The crystals generally grow fairly platelet-like, so sometimes you'll have to kind of cleave off some other parts to get a smooth surface, but it generally it really wants to be flat. Yeah. So the strong magnetic anisotropy favors the out-of-plane magnetization, and we have a Curie temperature of about 61 Kelvin in the bulk. So as I said before, it's fully magnetized with about 3 Bohr magnetons per chrome site, and so it has this out-of-plane easy axis and requires a rather large magnetic field to pull the moments in the in-plane direction. We performed bulk magnetism studies ourselves on the crystals that we grew, and they reproduced the literature magnetic data quite nicely. So now we want to know, how do they exfoliate? So we can mechanically exfoliate by cleaving the crystals thinner and thinner using Scotch tape, and then place them onto a silicon oxide silicon substrate. And so in this manner, we're able to obtain fairly thin crystals. However, unlike graphene and other air-stable materials, after just a few minutes in air, these crystals will rapidly hydrate and absorb water and eventually dissolve into puddles. So we quickly learned that an inert atmosphere is required to prevent hydration. So over the past several years, we've made a lot of efforts in our lab to develop techniques to fabricate devices from air-sensitive materials such as chrome iodide inside our glove box, since we can't use all of the conventional techniques performed out in ambient conditions. Once inside the glove box, we're able to identify crystals down to the monolayer limit of chrome iodide using optical contrast in the microscope images. And now we want to see, what does the magnetic order look like in few layer chrome iodide? So the first technique that we use to study 2D magnetism is the Magneto optical Kerr effect, or MOKE, which we performed in collaboration with Xiaodong Xu's group at the University of Washington. So the basic setup for MOKE is you take your sample, which has presumably an out-of-plane magnetization, and you shine in linearly polarized light normal to the surface. You then want to collect the signal of the reflected light, which will have a rotation in the linear polarization called the Kerr rotation. And this Kerr rotation is a very sensitive probe of the perpendicular magnetization. So it's just linearly proportional to your magnetic signal. And you can apply an out-of-plane magnetic field to change the magnetization in your sample and then track how the Kerr rotation responds. So when we do so with monolayer chromidide, we see this very beautiful ferromagnetic hysteresis loop. So this is consistent with an icing ferromagnet behavior where the spins are pointing perpendicular to the layer. And this is exactly what we would expect if we were to take a bulk ferromagnet and cleave it down to the atomically thin limit. However, we see something different when we look at bilayer chromidide. So here, the K-rotation actually vanishes at zero applied field and only gets a non-zero signal once we apply a much larger magnetic field. And then when we look at a trilayer flake, we return to a net moment at zero applied field. And so this result,
Yeah, I had a question too with magnetism. You have a thin magnetic field. Magnetism usually likes diamagnetic attractors. That's the name of it. I would like to lie in the plane and not point perpendicularly.
So the magnetic anisotropy in chromidide comes from the iodine ions because they have strong spin-orbit coupling.
Oh, so that what makes it.
So that's what gives rise to the strong anisotropy. Yeah, so it depends on the material. Yeah, so these results really confuse us at first because we expect to see a magnetic signal in the bilayer. And so what we ultimately came to understand is that ultrathin chromidide, unlike the bulk, is actually a layered antiferromagnet. So we can think of the ground state of the bilayer as having this layered antiferromagnetic up-down or down-up state. Yes?
Did you guys understand why magnitudes are a little different from first layer to third layer?
So some of it has to do with the spot size. So if the flake is smaller, then you're not covering the full area, whereas this flake was larger, so it was in the full. Correct. Yeah, it can vary sample to sample. So we can understand it as undergoing this switch once we apply a large enough field to polarize both layers with the applied field direction. So we then turn to another optical probe to further study chromidide. So in a similar setup, again with Xiaodong Xu's group at the University of Washington, we can use helical photoluminescence to read out the magnetic signal as well. So in this case, we excite the material using a laser, and then we collect the right and left circularly polarized components of the photoluminescence that are emitted from chromidide. And this difference in the right and left circularly polarized components is actually also going to be proportional to the out-of-plane magnetization. And again, we can apply an external magnetic field to change the magnetic states. And using helical photoluminescence, we're able to reproduce the same curves as we did with MOAK, which is consistent with our MOAK data and verifies this signal. So far, I've demonstrated that we can reliably grow bulk chromidide crystals. We can exfoliate chromidide down to the monolayer limit inside an argon glove box. And we've measured the magnetic order in few layer chromidide. However, some questions still remain. So can we control the magnetic order? Are there electrical probes of magnetism? Why is there antiferromagnetic interlayer exchange if the bulk is known to be a ferromagnet? And what about the other chromium trihalides? So next, I'm going to discuss ways to control 2D magnetism. So as I just showed you, bilayer chromidide undergoes this AFM to FAM transition with an out-of-plane magnetic field. So we wanted to ask the question, is there a way that we can electrically control this metamagnetic transition without just sweeping a magnetic field back and forth? And so the ultimate goal is to have electrical control of bilayer chromidide, which could have applications for magnetic memory, which rely on current or voltage control rather than sweeping a large magnetic field. And so ultimately, we'd want to be able to reversibly drive between these AFM and FM states, which you could think of in a memory situation as a 0 or a 1. So in order to do so, we fabricated these gated bilayer chromidide devices, where we have a bilayer chromidide flake and a graphite contact, 2 hexagonal boron nitride layers, which both protect the chromidide flake and also serve as dielectric layers, as well as a graphite top gate and a silicon back gate. And so here's an optical microscope image of the device, and here's the bilayer chromidide flake. And so in the absence of applying any gate voltages, we're able to see that we're able to reproduce the signals that we've seen previously with MOAK. If we apply a single gate voltage, we're able to see that we're able to change the transition in this material. So we're able to linearly tune this field of transition with the gate voltage. And if we look at the horizontal line cuts in this plot, that shows us that we have tunability by about plus or minus 0.2 Tesla. What's more interesting is if you look at the vertical line cuts. So here we're going to fix the field near the transition and then only change the gate voltage. When we do so, we're able to achieve gate control of the AFM-FM transition in bilayer chromidide. So here at different fixed magnetic fields, just by sweeping the gate voltage, we can go from a 0 K rotation up to a finite value and back and forth. So in order to better understand what's the origin of this transition, we can take advantage of the fact that we have two gates. So we have the graphite top gate and the silicon back gate. And what this allows us to do is to independently apply either a displacement electric field or control the doping in chromidide. So we can calculate what the constant doping line is as a function of top gate and back gate voltages, and then apply either doping or a displacement electric field. And so here I'm showing what happens in 0 displacement electric field at different constant doping levels. And you can see that we're able to change the magnetic field required to flip the spins in chromidide. When we have 0 doping but different constant displacement electric fields, there's no change in the signal. And so we conclude that the doping level seems to be what is controlling this metamagnetic transition in chromidide, but a further microscopic picture still needs to be studied. So far, I've shown that we have electrical control of 2D magnetism using a gate voltage, but we've only detected it using optical techniques. So we want to also have, for any practical application, to have some sort of readout of 2D magnetism using an electrical signal. And so one approach is to tunnel through the magnet, since the iodide is a magnetic insulator. So first I want to discuss what happens when you have electrical transport with several magnets present. So let's suppose that we have two ferromagnets separated by a non-magnetic spacer. And let's fix the magnetization in one layer and then have the ability to change the second magnetization to either be parallel or anti-parallel to the first. The resistance will depend on the relative alignment. So if they're parallel, then you'll have a low resistance state. And if they're anti-parallel, you'll have a high resistance state. And so this is called the giant Magneto Resistance effect, or GMR. And this was responsible for the 2007 Nobel Prize in Physics. And so this is actually used in a lot of common electronics that we are familiar with in our everyday lives, such as the read head on the hard disk drive. So on a hard disk drive, there are many magnetic memory elements. And the way that they are read off is that at the very tip, if you zoom in, you can see a little GMR read sensor. And whether it detects a high or low resistance, you can then read out that location's magnetic memory element as a 0 or a 1. So this GMR device is one geometry for a magnetic tunnel junction. But then there's also another geometry that you can imagine that also has this same principle where the tunneling resistance depends on the magnetization. So in these spin filter magnetic tunnel junctions, you have two non-magnetic metals as the electrodes, but then the tunnel barrier itself is magnetic and can be changed. So since chromidide is a magnetic insulator, we wanted to take a look at these kinds of devices. So in spin filter magnetic tunnel junctions, you tunnel electrons through the magnetic barrier as a function of magnetic field, and then measure the current and voltage response. So this underlying effect is called the spin filter effect. So if you imagine having a paramagnet as your barrier and you send in a non-spin polarized electrical current, then since the spin up and down electrons have the same tunnel barrier height, then you'll have no spin polarization above the Curie-Néel temperature. If you then cool down below the magnetic ordering temperature, then if you have a ferromagnet, then the spin up and spin down bands will be split in energy. And then the barrier height depends on the electron spin polarization. Since there's a spin-dependent tunneling probability, you'll end up with a spin-polarized current on the other side. And so you'll preferentially end up with spin-up electrons in this case compared to spin-down electrons. You can then take this idea of the spin filter a step further and have a double spin filter magnetic tunnel junction, where here the resistance will depend on the relative magnetization of the two magnetic layers in your barrier. And just like with GMR, you'll have a low resistance when the magnetizations are parallel and a high magnetization when they're anti-parallel. And this has been pioneered by Jagadish Mudera's group, also at MIT, using europium sulfide layers separated by an aluminum oxide spacer. And you can see that they're able to switch between a high and low resistance states by applying an in-plane magnetic field to switch these two magnetizations. So we then adapted this idea to the van der Waals case, where we can use two graphite layers as the non-magnetic electrodes. And due to the van der Waals nature of chromidide, we don't need to use a spacer layer because the van der Waals gap will actually just serve as this decoupling between the two layers, say in a bilayer flake. And so we should, in principle, be able to treat bilayer chromidide as a double spin filter and then be able to read out electrically whether we're in the AFM or FM state as we apply an out-of-plane magnetic field. So we fabricated these van der Waals heterostructures inside our glove box, where we use top and bottom boron nitride to encapsulate our device, and two graphite contacts, which we aligned such that the only overlap area would be through the chrome iodide barrier, so that electrons have to tunnel vertically through a barrier that we fabricated to be 2 to 4 layers thick. So first, let's take a look at what happens as we cool down one of these devices. So as we cool down in zero field, we see that the junction resistance has a kink right around the Curie temperature of the bulk, which is consistent with magnetic ordering in the barrier. Furthermore, we see that the resistance increases as we cool down below this temperature, and this increased resistance with magnetic ordering is suggestive of antiferromagnetic coupling, because you can think of the spin filter effect as filtering out spins in opposite directions between adjacent layers, which will result in a lower overall resistance compared to the paramagnetic state above 61 Kelvin. Now, if we looked at the zero bias conductance as a function of magnetic field for bilayer chromidide, we see this very discrete step between low and large applied magnetic fields. And so what these two states are is the direct electrical detection of the AFM-FM transition in chrome iodide. And as we sweep the field in the opposite direction, we see similar results. We can try to understand this Magneto resistance by looking at a simple double spin filter picture. So in the antiferromagnetic ground state, both spin up and spin down electrons both have to tunnel through a tall and small barriers, and this leads to overall low conductance or high resistance. And in contrast, in the fully aligned state, the spins that are pointing spin up and aligned with the barrier have a very easy way to tunnel across, and this will give rise to an overall increased conductance and increased spin polarization through the barrier. So we can then look at the bilayer data and estimate that the spin polarization in this fully aligned case is close to 85% based on our simple model. So you may be asking the question, can we then increase the spin polarization further by adding even more layers? And the answer is yes. So in a 4-layer chromidide junction, we have a much larger zero bias Magneto resistance of 550%. And based on our model, we're estimating that the spin polarization is quite large, up to 99%, though this is an approximation, in this fully aligned case. And our collaborators in Xiaodong Xu's group actually observed that at finite bias, you can get very, very large Magneto resistance in 4-layer magnetic tunnel junctions of up to 19,000%. So these simple magnetic tunnel junctions using chromidide could potentially be used as a source of on-chip spin polarized current, which could be of interest to the spintronics community. So far, I've only shown you what happens at zero bias in our devices. So now we want to ask the question, what happens when we apply a small finite bias? So if you have a small or zero bias, then you'll only have elastic tunneling of electrons from one graphite to the other. So there's no gain or loss of energy. However, when you apply a bias between the two electrodes, you open up inelastic electron tunneling pathways in addition to the already existing elastic pathways. And what this is from the electrons being facilitated across the barrier by tunneling pathways from collective mode excitation, such as phonons or magnons in the barrier. And what this results in is an increase in the conductance once the bias energy exceeds the collective mode excitation for that mode. And so there are several experimental signatures for inelastic tunneling spectroscopy. So if you measure just the DC current as a function of bias, you'll see a slope change at this energy. If you look at the differential conductance as a function of bias, you'll see a step. And then if you take the derivative of that, you can see it even more clearly as peaks in the spectrum. So back in the early 1970s, researchers looked at a nickel oxide magnetic tunnel junction, and they noticed these little humps in the inelastic electron tunneling spectroscopy. And when they overlaid it with the magnon density of states, they realized that they're actually observing magnons in their tunnel barrier of nickel oxide. So if we take a look at our own tunneling data, then we can actually see that it's quite similar. We see these little features that then if you take derivative of the data, you can see emerging much more strongly as peaks. And what's more interesting is that when we looked at how these peaks evolved in a magnetic field, we see that they seem to be dispersing somewhat linearly with the magnetic field. In order to understand these better, we can think of what happens to the spin excitations in chromiodide. So if we start with a monolayer of chromiodide, since the moments are localized on the chromium sites, we can ignore the iodine. And then we can think of what happens as a magnon propagates in this lattice. So what you can model this as is a spin 1 boson or magnon hopping on a honeycomb lattice. And this may look a little familiar to you if you've looked at graphene before, of electrons hopping on a honeycomb lattice of graphene. And so this is an analogy to Dirac magnons. Our theory collaborators, Jose Lado, David Soriano, and Joaquin Fernandez Rosier, performed some calculations of what Dirac magnon energy should be in chromiodide. And using their Heisenberg Hamiltonian, they estimate that the density of states should look somewhat in the region of our magnons, of our inelastic electron tunneling spectroscopy of chromiodide. And so if you overlay some of their calculations with our features, it's highly suggestive that we are observing Dirac magnons in chromiodide. So now I want to return to the mystery of this magnetic behavior in ultrathin chromiodide compared to the bulk. So why is ultrathin chromiodide going to be antiferromagnetic if the bulk is ferromagnetic? And namely, what about the other chromium trihalides? So we wanted to investigate in chrome chloride whether we also would see some interesting behavior as we cleave it down to the ultrathin limit. So chrome chloride is a layered antiferromagnet, so it has the same crystal structure as chromiodide, but this time the moments still localized on the chromium sites will be aligned within the plane. So each layer will be a ferromagnet, and then you'll have antiferromagnetic interlayer coupling. It undergoes the stacking phase transition from the monoclinic stacking to the rhombohedral stacking at about 240 Kelvin. And its bulk magnetization shows an AB plane, easy plane, where the moments can saturate in a given direction within the plane with a very, very small applied magnetic field of only 0.2 to 0.25 Tesla. So we wanted to ask the question, is this magnetic behavior the same as we take it down to the few layer limit? In order to study chrome chloride, we again turn to the magnetic tunnel junction as a way to probe its magnetic ordering. So again, we're going to use top and bottom boron nitride and 2 non-magnetic graphite electrodes, and then use the tunnel barrier, this time of chrome chloride, that's 2 to 4 layers thick. And this time, we're going to apply an in-plane magnetic field and use the Magneto Resistance to measure the interlayer exchange coupling as we try to polarize this antiferromagnet to be in a fully aligned state with the magnetic field. So the basic idea here is that we start out in the antiferromagnetic ground state, which is the anti-parallel high resistance state. And then as we apply a magnetic field in a given direction within the AB plane, the spins in both layers will begin to cant towards that field. And once we reach the saturation field, the spins will be fully aligned. And so now we'll have a low resistance parallel state. And so we'll be able to use the Magneto Resistance to read out where the saturation field is, because we should see a plateau once we reach this low resistance state. So first, we can look at the temperature dependence as we cool down one of these devices as a check. And so we see that the DIDV decreases below the nail temperature with a little kink here, indicating the onset of antiferromagnetic order. So far, it looks like a layered antiferromagnet, just like the bulk. We can also take a look at the temperature dependence of the magneto resistance in these junctions, and we see that the magneto resistance vanishes roughly above the nail temperature of chrome chloride. So far, it looks just like bulk chrome chloride.
It looks like a stack of layers. What's that?
We were taking 1 Kelvin increments, such as
okay.
the color scale. Yeah. So far, it looks just like what we would expect for the bulk until you start to look at the magnetic field scales of this magneto resistance. So here I'm showing the magneto resistance for 2, 3, and 4 layer devices as a function of in-plane applied magnetic field. And just to normalize them onto the same scale, you can see that these saturation fields indicated by the dashed lines are much larger than what we would have expected based on the bulk chrome chloride data. So the bulk saturation field is all the way down here, yet we're seeing that it's much harder to polarize the spins in the same direction in these few layer limit, indicating that there must be some larger antiferromagnetic exchange between the layers when we go down to the thin limit. So we want to try to extract the interlayer exchange using a model. So we can consider 2 contributions to the energy in these systems, where we can first look at the interlayer exchange energy. So if we consider 2 adjacent layers, because they're antiferromagnetically coupled, there will be an energy penalty if they're aligned in the same direction. And then as we apply an in-plane magnetic field, there will be a Zeeman energy term which will give a negative contribution to the energy because it's favorable to have the layer align with the applied field. And so it's this competition between these 2 energies that will ultimately tell us what the saturation field is in terms of the exchange. And so we can now minimize the total energy per unit area and then roughly relate the external field or the saturation field with the exchange. So in the simple case of bilayer, we can consider looking in the AB or XY plane. And here we can approximate each layer as having a single moment, so M1 and M2 for the 2 layers. And we can apply an external magnetic field in the x direction. And so we can just write down from trigonometry with these vectors what these energy contributions are. And then we can minimize the total energy and find this simple relation relating the external field to the exchange. And then in the case where we've reached saturation, we just set phi to equal 90 degrees for both of these layers. And then we have this, we find that in bilayer, the saturation and exchange should be the same. And then in trilayer and 4-layer, there's just a numerical prefactor. So now we can just write down these models and then extract the interlayer exchange value from the saturation. And what we find is that the interlayer exchange is about the same for our 3 different device thicknesses, but more importantly is a factor of 10 greater than the interlayer exchange in the bulk. So for some reason, we're seeing a 10-fold increase in this interlayer exchange in ultra-thin chrome chloride. So to summarize the mystery of the magnetic order in the chromium trihalides, bulk chrome chloride has a small antiferromagnetic coupling, which increases by a factor of 10 in the few limit. Bulk chrome iodide is a ferromagnet, yet we and many other groups have observed that few layer chrome iodide is an antiferromagnet. So this has gained a lot of attention over the past several years, especially in chrome iodide, which has been studied for longer. And there have been many papers on the archive trying to speculate as to why this is occurring. And so the dominant term that will stick out is stacking. So there's a hypothesis that the stacking order in the chromium trihalides is what is giving rise to this difference in the interlayer exchange. So this paper published last year in Nanoletters considered calculations where you look at the interlayer interactions mediated by the chromium iodide iodide chromium super exchange mechanism, or namely just the exchange between nearest neighbors of chromium sites across the van der Waals gap through the adjacent iodine ions. And what they found is that if you shear one layer with respect to one another in chrome iodide, you can actually tune between favoring a ferromagnetic or antiferromagnetic interlayer exchange based on the stacking between 2 layers. And so we wanted to ask the question, can we experimentally verify the stacking hypothesis in chromium trichloride? So one way to analyze the stacking symmetry is to turn to Raman spectroscopy. So we looked through the literature and identified that in bulk chrome chloride, it's been seen that there's this mode in the Raman spectrum at 247 wave numbers that undergoes a shift in energy by about 2 wave numbers at 240 Kelvin right at the stacking transition, where it goes from the monoclinic phase at high temperatures to the rhombohedral phase at low temperatures. And then we took the spectrum ourselves and saw that this is quite a nice peak that we can easily study in the bulk and thin limits. So first, when we measure our bulk Raman spectrum, we see right at 240 Kelvin in the dashed line, we see a jump in the energy by about 2 wave numbers. However, when we looked at thinner exfoliated flakes, we saw that not only was there no transition at 240 Kelvin, but in this sample, we even measured down to 10 Kelvin below the nail temperature and saw no evidence of this phase transition occurring. So this led us to ask, does this mean that thin chrome chloride is remaining in the monoclinic phase even down to low temperatures below its magnetic ordering? So one way to analyze this is to look at the symmetry of this peak that we've been studying. So if you consider the peak energy as a function of Raman polarization angle, in the rhombohedral phase, this peak is actually a set of 2 degenerate phonon modes. So as you change the Raman polarization angle, you'll change the relative intensity between these 2 modes, but since they're degenerate, the overall peak that you actually observe will have no polarization dependence in the energy. However, in the monoclinic phase, these phonon modes are actually split slightly in energy, and therefore, as you modulate the Raman polarization angle, the relative intensities will change, and thus the overall peak that you see will actually be shifting slightly in energy. And so you can work out using Raman tensors that this will give you a 4-fold peak energy oscillation as you sweep the polarization angle from 0 to 360 degrees. And so we can see this in our raw traces here in bulk sample at 300 Kelvin. And so we can look at the peak energy shift as a function of polarization angle. And so in bulk at 300 Kelvin, we see this 4-fold pattern consistent with what we expect for a monoclinic symmetry. As we cool down below the phase transition, we see that this symmetry has nearly vanished. In contrast, when we look at a 17 nanometer flake, we see this 4-fold pattern quite strongly at 300 Kelvin, and we still see it quite strongly even down to 80 Kelvin, well below the expected phase transition at 240 Kelvin. We've also measured this down to 10 Kelvin and see that this 4-fold pattern still remains in exfoliated flakes. Thus, on the basis of temperature and polarization-dependent Raman, we conclude that while bulk chrome chloride undergoes this stacking change from monoclinic to rhombohedral, ultrathin chrome chloride remains pinned in the monoclinic phase at all temperatures. We further collaborated with Tim Kaxiris's group here at Harvard with Daniel Larson and Shang Fang in order to look at DFT calculations for chrome chloride, similarly to what was done for chrome iodide. So what they did was they looked at the energy difference between the ferromagnetic and antiferromagnetic states as a proxy for the antiferromagnetic interlayer exchange. And so they looked at both the monoclinic phase and the rhombohedral phase and used a large number of different DFT methods. But what they found is that regardless of the DFT method used, the energy difference between the monoclinic and rhombohedral phase always showed a larger antiferromagnetic exchange for the monoclinic stacking. They further performed calculations where at fixed layer spacing, they sheared one layer with respect to one another. And they again found that the monoclinic phase, shown here in the black star, has a larger antiferromagnetic exchange than the rhombohedral shown in the white star. And so this supports our larger antiferromagnetic exchange for the monoclinic phase, which we believe ultrathin chrome chloride to remain in down to low temperatures. There's been a lot of other evidence in the literature supporting the stacking order in transition metal trihalides is important for the magnetic order. So in this one paper published a few years ago, they took alpha ruthenium chloride bulk crystals, which are similar in structure to the chromium trihalides, and they repeatedly bent the crystal back and forth. And what they found was that with successive bending, they were able to shift the nail temperature from 7 Kelvin up to 14 Kelvin. And they attribute this to introducing stacking faults between the layers in this bulk crystal, which one can think of as similar to the mechanical exfoliation process of our bulk crystals as we cleave them down to the few layer limit. There's also been some very nice work on second harmonic generation of bilayer chromidide at low temperatures, and the symmetry patterns that they observe are consistent with the monoclinic symmetry at low temperatures, and further also rules out rhombohedral symmetry, which would require a C3 symmetry axis and a threefold pattern in their signals. There's been more work on chromidide stacking. So this work, scanning NV magnetometry by Patrick Malatinsky's group, accidentally punctured a 9-layer flake of chromidide, but fortunately they were able to get the signal before and after the puncture, and they noticed that the magnetic signal greatly increased after puncturing, and there was also a shift in the Raman signal. So they attribute this to relaxing locally the crystal to a different phase and then inducing this AFM to FM transition. So presumably this is due to the stacking change from the monoclinic to rhombohedral. There's also been work more recently on the archive by both Xiaodong Xu's group and Qinfei Mac's group at Cornell on pressure-induced chromidide stacking change, where they take a bilayer chromidide magnetic tunnel junction and place it in a diamond anvil cell and apply pressure, and then they're able to irreversibly change the crystal from the antiferromagnetic coupling to the ferromagnetic coupling. So this is further evidence that we are really depending on stacking for these magnetic changes in the bulk to ultra-thin chromium trihalides. So to summarize, the chromium trihalides are a class of 2D magnetic insulators that can be cleaved down to the monolayer limit where magnetic order still remains. We have one member, the ultra-thin chrome iodide, a layered antiferromagnetic phase compared to the bulk. And in this system, we've been able to demonstrate both electrical readout and control of the 2D magnetic states in this material. We also have ultra-thin chrome chloride, which has a 10-fold antiferromagnetic interlayer exchange increase compared to the bulk, and which has been very illustrative in showing how stacking and magnetic orders are strongly linked. Moving forward, now that we have 2D magnets at our disposal, we can begin to assemble van der Waals heterostructures that incorporate these magnets. So some earlier work by Xiaodong Xu's group shows proximity magnetism in a monolayer tungsten diselenide heterostructure placed on top of a thick slab of chromium iodide. They're able to observe valley splitting due to proximity magnetism from the underlying magnet. We can also begin to explore van der Waals spintronics using magnetic tunnel junctions to both generate and detect spin polarized currents. Qinfei Mac's group showed earlier this year the first bilayer chromidide spin transistor, in which in a magnetic tunnel junction, they were able to both use a gate voltage to switch between the antiferromagnetic and ferromagnetic states, and then read this out electrically by measuring the conductance through the barrier. Furthermore, since we've now developed different techniques to both handle and fabricate devices of air-sensitive materials within our glove box, as well as new readout techniques to measure magnetism in the ultra-thin limit, we can now start to explore the wide variety of different materials that are both magnetic and predicted to be cleavable due to a van der Waals gap. And these could have some very exotic new phases of matter, including the Kitaev quantum spin liquid state and alpha ruthenium chloride, as well as to start to study more exotic physics like Dirac-Magnon interactions and honeycomb ferromagnets, which could be potentially found in these number of materials. So there's really a lot of room to grow for 2D magnets as we continue to exfoliate new materials, and I'm excited to see where this takes us. So I'd like to thank the many people who have been involved in these projects over the past several years. So within our group at MIT, I'd like to thank David McNeil, a postdoc who has worked on both chrome iodide and chrome chloride and has been very important for all of these studies, as well as a friend of Ara Morataya, a former postdoc who set up the glove box and growth capabilities in our lab and was also instrumental in the initial studies on chrome iodide. I'd also like to thank Ricardo Koman for Raman over at MIT, as well as Xiaodong Xu's group at the University of Washington for our many collaborations together. I'd like to acknowledge our theory support from Joaquin Fernandez-Rosier at INL, as well as Tim Krexieras here at Harvard. I'd like to thank our BN crystal growers and our many funding acknowledgements, including CIQM. And I'd like to thank all of you for your attention and be happy to take any questions.
Okay, thanks for a very nice talk with a lot of things in it. Questions? I have one to start with. If I'm thinking at undergraduate level, say, if you're looking at many layers of the chromium chloride and thick, and then it undergoes this phase transition, where like the entropy must matter at high temperatures, right? And then it lines up, and then it goes away at low temperatures. But if it really were just purely two-dimensional things that didn't see each other, that wouldn't happen, right? Because they would just look like a collection of 2D systems. Do you have a feel in terms of if you wanted to design a small system where you're stacking up layers, what you would, am I making sense or not? Maybe not. But if you stack them up, what could you do to sort of induce different types of having them line up, or the ways that you can change that? What's the physics sort of involved?
So I guess the translational, I guess they have freedom to translate with respect to one another.
Right.
One thing that we haven't explored yet, but could be interesting, is to explore twist angle. So if you were to
Right.
take, say, two monolayers or two bilayers and twist them with respect to one another, do they stay in some metastable state different from what is intrinsically seen? There has been some MBE grown 2D magnets. So recently, chromium tribromide, another chromium trihalide, was grown by MBE, and so that demonstrated all sorts of different stacking orders from the bottom-up growth. But I think it might be hard to achieve some of those if you start with the bulk crystal and go from there.
Yeah, good, thanks. Other questions?
It's a very good talk. For the GMR research, if you switch the states, did you guys explore how fast this dynamics can happen?
We have not looked into the dynamics of the switching speeds.
Other questions? Okay, if not, let's thank her again.